Hi everybody, it's time for us to look at another awesome data structure, and this time around we're going to look at the binary search tree. Now a binary search tree builds upon binary trees by adding some very important logic, and that logic is around making the tree efficient for both storing data and retrieving data. So we're going to learn a whole lot about that and more in this video, of which there's going to be two parts of this video. The first part is going to be on how we add data to a binary search tree. The second part will be on how we remove data from our binary search tree, and we'll get to that in a few moments. But before I go further, I should let you know that if you want a friendly yet comprehensive look at the data structures and algorithms and all about trees, including the binary search tree, check out my best-selling book, Algorithms, Absolute Beginner's Guide, available in both online bookstores and physical bookstores in paperback and Kindle editions. Link below on how you can get more details on that. Now, let's get back to the star of this particular video, which is the binary search tree. If we squint a bit and take many steps back, a binary search tree, as you will see in a few moments, will look a whole lot like a binary tree. Binary trees are pretty good. They set a solid foundation for us with their nodes and edges and various rules on what makes a perfect binary tree and a balanced binary tree and things like that. And where binary search trees come in is they add that all-important logic to make storing them, data into them, very efficient, and retrieving data very efficient as well. When we looked at the implementation of a binary tree earlier, we kind of saw that we could add any value we wanted to the various nodes, and we can just keep adding nodes in any form that we want, which is great to store data, but it may not be the best way for us to retrieve data and organize our data later on. And that's really where the binary search trees comes in. And so with binary search trees, there's a very simple rule, or two rules actually, and we're going to see that in multiple forms with a little bit more detail at each layer. But at a very first high-level introduction of it, a binary search tree has this simple rule where nodes with smaller values go left and nodes with larger values go right. Just memorize that for now in terms of small value, go left, larger value, go right. And we'll look into details of how that plays out when we're adding and removing nodes from it. So take a moment and take a look at this tree right here. This is a binary search tree, and it's a proper binary search tree. It has all the right values in all the right places. Notice that at each node, starting with the root of 67, let's pay close attention to node values and the values of the children. At each layer, notice that the child node to the left is less than the parent node's value, and the child node to the right is greater than the parent node's value. And this happens with every node at every layer, unless you're at a leaf node where there are no more children. And you can see here, 67, 35 is less, 73 is large. 35 is to the left of 67, 73 is to the right of 67. Let's look at a 35 node. 20 and 39 are its two children. We can see that 20, I kind of skipped the node there somehow. 20 is to the left on 35, 39 is larger, so it's to the right, and every node kind of follows the same pattern. And so if we take many steps back, a tree is a data structure, a binary search tree is a data structure as well, just like our arrays, stacks, queues, linked lists, and more. It's just that we have some extra values and some logic to make sure the values go in the right places. And so the best way to learn about how a binary search tree works is to actually start building one from the ground up. And so here's what we're going to do. We're going to start with an empty binary search tree and build our knowledge on how to work with them from there. So it gets us to the part one, which is how do we add nodes to a binary search tree? So right now, it doesn't look like much of a tree. We have a root node, it has a value of 42. And that is a good point to start. Hitchhiker's Guide to the Galaxy calls 42 like the greatest number on Earth, or something more different. I forget the exact wording of it. So we're going to start with 42. So next what we want to do is this. We want to add the number 24. So 24 is now going to be added to our binary search tree. Now the question is, where does it go? Does it go left of 42? Does it go right of 42? So that goes back to what we started with earlier. If the value we're adding is less than the parent node, the value goes left. It becomes a left child. If the value we're adding is greater than the parent, the value goes right. It might be a right child. Now, we won't always be a child, but for now it will be a child because we're the root node. So in this case, we know that 24 is less than 42, so it goes left, and it now becomes a child on the left side of 42. So we have a binary tree at the end of the day, and the left child happens to be 24, but because of the ordering, it's a binary search tree. So now let's add another number. Let's add 99. Where would 99 go? We know that 99 is greater than 42, so it becomes the right child, and it's greater than where we are before. And so now we have 42 with left child 24, right child 99. So the thing is, we're not going to be done adding more numbers. We're going to go a little faster as part of how we're going to do this. So now we want to add one more node. We want to add 15 as its value. In this case, where does 15 go? We look at 42, we always start at the root, we start at 42. 15 is less than 42, so we go left. What is 24? Well, 24 is also going to be greater, in this case 15 is less than 24, 24 is greater than 15, so because 15 is less than 24, we go left again. And there's no more node to compare against, so 15 now becomes the left child of 24, and we're currently at the right location. So next, let's add the number 50. 50 is greater than 42, so we go right. 50 is not greater than 99, needs to go left. And again, there's no child here. There's a leaf node, 99 is a leaf node, so 50 now becomes a child of 99 on the left-hand side. Let's go faster. We're going to go much faster now in adding nodes, because I want us to get mentally, accustomed to quickly looking at a binary search tree and knowing exactly where a node ultimately belongs. 120, you want to add 120 to this list. 120 is greater than 42, we go right. 120 is greater than 99, we go right again. No more children, so 120 now becomes the right child of 99. Next number we want to add, 64. 64 is greater than 42, so we go right. At 99, is 64 greater than 99? It is not, so we go to the left, we travel left, we're at 50. Is 64 greater than 50? It is. There's no other nodes here, so 64 now becomes the rightmost child of 50. And so we're in a good spot there. Now, we can continue on adding more and more nodes, but you start to see the pattern emerging. They're following the idea of if a node is smaller, you go left. If a node is larger, you go right. And so we're going to look at the next stage of how to remove nodes in the next video. And so if you have any questions, by all means, ask in the forums at forum.crypto.com, where I and others would be happy to help you out with all your questions about just general development, including algorithms and data structures, and of course your binary search trees as well. And before I wrap this up, here's some quick actions you can take to go deeper into the topics that we talked about right now, or just keep up with all the content I regularly share. And with that, I will see you all next time.